Okay guys, Professor Doney once again. We're looking at vertical motion in one dimension, and we're looking at the launch problem or throw up problem, we sometimes call it, where the object comes back down but it lands at a different height than where it was launched. This situation, whether we throw it up here and it ends up landing on a rooftop, okay, or we're standing up on the castle and we throw things up and they come back down and land below us. So they have a different launching and landing height in those situations. This would be if you're in the castles, this would be storming the castle. You're trying to throw stuff into the castle. This is the people in the castle obviously throwing stuff on you. So let's look at this first one just to get started. So what we're going to do is launch the object up. Let's use 30 meters per second as we had in the last problem. And it goes up and it's going to land above here, and we're told that it lands, I don't know, on a building or on a rooftop that's 20 meters above where we launched it from. It's about the third, a little over the third floor if you're looking at a building. So we throw it up, it goes past the roof, and then it comes back down and lands on the roof. So the way we're going to treat this problem is kind of unique. The book would go through, or most books that I've seen will go straight through and solve this using the delta y equation, which is a perfectly valid way to do it. What they're going to do is put in 20 meters here as the distance, initials 30 times time, half minus 9.8, and then t squared. What happens with this problem though is we end up with like 4.9 t squared minus 30t plus 20 equals 0, and that actually is a quadratic equation. Okay, now unless you've dealt with quadratics before, they can be very messy even if you use the solution equation, and there's lots of places to make mistakes. So my preference is not to do it that way. You can if you understand it and you're good with the math. What I'm going to do is break it up, the up part and the down part. The up part we're going to treat as a launch problem, and the down part we're going to treat as a drop or free fall problem. Okay? So what we're going to do is throw it up at 30 meters per second. I'm going a little fast here because I'm at a 5-minute time limit. And once we find out how far it takes to go up and how long it takes to come up, then we're going to let it drop from that height, because we know the initial velocity will be 0 once we drop it, and we let it fall just that distance till it hits the building. So if we go through this is the same as the throw up problem we just did. We'll find out that t up is, well, 306 or 3.1 seconds. We'll also find out that y up, I believe, was, what was it? Hang on. 46 meters, that's right, if I look back at that one. So when we get to the second part, I'm just going to do the second part here. The launch part we've already done in a previous problem. The second part is when we drop it, what we're going to do is drop it from 46 meters, but it's only going to fall 46 minus the building height, which is 20, so it really only falls back 26 meters. So what we're going to do is do a drop from 20 meters, and that'll be this equation, gt squared, and we put 26 in here. Initial velocity 0 from the top, half 9.8 positive, and then t squared. If we go through that, we're in a space here, we're going to get 26 divided by 4.9. We take the square root of that. It tells us it takes 2.3 seconds to fall. The total time in the air is going to be the 3 seconds, or 3.1 up, plus the 2.3 back down. That gives us a total of what, 5.4 seconds in the air. So that's a quick way how to solve it. I know I went quickly. I just want to say that I like to break it up and treat it as the launch problem and do that, and then put it together with a drop on the other side and feel it's easier. So hope that worked out for you.